Hello students, in this video we are going to see Canter's intersection theorem. Statement of theorem is let XD be complete metric space. Let XD be complete metric space and sequence Fn n runs from 1 to infinity be sequence of non-empty closed subset of X such that first one is F1 contains F2 contains F3 contains and so on. Second one is diameter of Fn tends to 0 as n tends to infinity. Then intersection Fn n runs from 1 to infinity contains precisely 1 point. In statement we have given that XD be a complete metric space. What is complete metric space? XD is complete metric space when every Cauchy sequence Xn or every Cauchy sequence in XD is convergent. Then XD is a complete metric space. And sequence Fn be a sequence of non-empty closed subsets of X such that F1 contains F2 and so on up to, that is, sequence Fn is a decreasing sequence. And in second part we have given that diameter of Fn tends to 0 as n tends to infinity. Then we have to show that intersection Fn contains precisely 1 point. That is, we have to show that intersection Fn contains only 1 point. Okay, let us see proof of this theorem. Proof: let Xn belongs to Fn for all n belongs to set of all natural numbers. Then sequence Xn is a sequence of points in XD such that xn plus 1, xn plus 2 and so on belongs to Fn for all k is greater than or equal to n. Why this is? Because sequence Fn is a decreasing sequence. That is, F1 contains F2 contains F3 and so on. That means xn, xn plus 1 and so on belongs to Fn. Moreover, distance between xn and xn is less than or equal to diameter of Fn for all n comma m is greater than or equal to capital N. Obviously, distance between xn and xn is less than or equal to diameter of Fn, because diameter of Fn is nothing but superior of distance between xn and xn. So distance between xn and xm obviously less than or equal to superior of d of xn comma xn. As xn comma xn belongs to Fn and for all n comma m is greater than or equal to capital N. In hypothesis, we have given that diameter of Fn tends to 0. Since diameter of Fn tends to 0 as n tends to infinity, since by condition 2. Okay. Therefore, for given epsilon greater than 0, there exists positive integer n such that the diameter of Fn minus 0 is strictly less than epsilon for all n is greater than or equal to n0 by definition of convergence. So call this equation number 2 and this is equation number 1. From 1 and 2, what is equation 1? Equation 1 is d of xn comma xm is less than or equal to diameter of Fn, and 2 is d of Fn minus 0 is strictly less than epsilon. So from 1 and 2 we will get distance between xn and xn is strictly less than epsilon for all n comma m is greater than or equal to n0. That implies, this is the definition of Cauchy sequence, that implies sequence xn is a Cauchy sequence, in capital X. In hypothesis, we have given that XD is a complete metric space, and in complete metric space, every Cauchy sequence is convergent. Since XD is a complete metric space, we know that in complete metric space every Cauchy sequence is convergent. Therefore, sequence xn is convergent in XD. Therefore, limit n tends to infinity, xn is equal to x. Suppose this sequence is converges to point x, and this x obviously belongs to capital X. Call this equation number 3. Now, sequence xn plus 1 and so on is a subsequence of sequence xn and runs from 1 to infinity such that xk belongs to Fn for all k is greater than or equal to n. For all k is greater than or equal to 1. Therefore, sequence xn is a sequence of points in Fn for all n. Therefore, sequence xn is a sequence of points in Fn for all n. Moreover, subsequence of convergent sequence has same limit. Therefore, this subsequence converges to x. Therefore, limit k tends to infinity, xn k is equal to x, which is belongs to Fn closure for all n. Therefore, x is belongs to Fn for all n. Since each Fn is closed. Therefore, x is belongs to intersection Fn, because x is belongs to Fn for all n. That means x is belongs to F1, x is belongs to F2, and so on. Therefore, x is obviously belongs to intersection Fn. Therefore, intersection Fn contains at least one point. Now we have to show that intersection Fn contains exactly one point. So, if xy belongs to intersection Fn, then x and y belongs to Fn for all n. Zero is less than or equal to d of xy is less than or equal to diameter of Fn, which tends to 0 as n tends to infinity. D of xy is less than or equal to d of Fn, because in condition 2 we have given that diameter of Fn tends to 0. That implies distance between x and y is equals to 0. That implies x is equals to y. Therefore, intersection Fn contains precisely one point. Hence, proof of theorem is completed. Let us see examples. Example 1. Give an example of sequence Fn of non-empty subspace non-empty subset of complete metric space Xt such that F1 contains F2 contains and so on, and diameter of Fn tends to 0 but intersection Fn is equals to 5. Okay. Solution: in Ru, take Fn is equals to open interval 0 1 by n. First, we have already seen that Ru is a complete metric space. Second, F1 is equals to, put here n is equals to 1, so you will get F1 is equals to 0, open interval 0 1, contains F2 is equals to open interval 0 1 by 2, contains F3 is equals to open interval 0 1 by 3, and so on. Here observe that diameter of Fn is equals to 1 by n. Okay, diameter of Fn is 1 by n. Diameter of Fn means superior of distance xn, xn, which is equals to diameter of Fn. For Fn, superior distance will be 1 by n minus 0. So you will get 1 by n. And this 1 by n tends to 0 as n tends to infinity. Okay. But intersection of Fn is equals to 5. Why? See here, F1 is open interval 0 1, F2 is open interval 0 1 by 2, contains open interval 0 1 by 3, and so on. Open interval 0, as n tends to infinity, this 1 by n tends to 0. So you will get this interval, open interval 0 0, means here this interval contains no point, so intersection Fn is 5. Let us take second example. Give example of sequence of non-empty. Give example of sequence of non-empty closed subsets of metric space, Xd such that F1 contains F2 contains and so on, and intersection Fn is equals to 5. Solution: in complete metric space Ru, take Fn is equals to semi-closed open interval n infinity, is closed for each n, and F1 contains, F2 contains, F3 and so on. But diameter of Fn does not tend to 0 as n tends to infinity, and intersection Fn is equals to 1. Okay. Let us see converse part of Canter's intersection theorem. In a metric space, every decreasing sequence Fn of non-empty closed set with diameter of Fn tends to 0 as n tends to infinity has exactly one point in its intersection, then XD is complete metric space. Let us see proof. In this theorem, we have given that in a metric space, every decreasing sequence Fn of non-empty closed set with diameter of Fn tends to 0 as n tends to infinity has exactly one point in its intersection, then XD is a complete metric space. Okay, that means here we have to show that XD is a complete metric space. That is, we have to show that every Cauchy sequence in XD is a convergent. So first, let sequence Xn be a Cauchy sequence in metric space XD. Therefore, by definition of Cauchy sequence, for all epsilon greater than 0, there exists n0 belongs to set of all natural numbers such that distance between Xn and Xn is strictly less than epsilon for all m comma n is greater than or equal to n0. Call this equation number 1. Take Gn is equals to sequence Xn plus 1 and so on for all n. Okay. Then by 1, here is Gn. Then by 1, diameter of Gn bar is equals to diameter of Gn converges to 0 as n tends to infinity. See here, Gn is nothing but the subsequence of this sequence Xn, and this sequence Xn is a Cauchy sequence, means d of Xn comma Xn is strictly less than epsilon. So if we choose epsilon is equals to 0, then obviously d of Gn tends to 0 as n tends to infinity, where Gn bar closed subset closed subsets of metric space XD. That's why Gn bar is equals to Gn, such that G1 bar contains G2 bar, G1 bar contains G2 bar, contains G3 bar, and so on. Okay. Take Gn bar is equals to Fn. By hypothesis, intersection Fn contains, or intersection Gn bar contains single point X, then distance between Xn and X is less than or equal to diameter of Fn, which tends to 0 as n tends to infinity. That implies Xn converges to X, and this X belongs to capital X. Therefore, X is the limit point. Of Gn bar. Therefore, X is the limit point of Gn bar. Therefore, that means Xn is convergent in X. Therefore, every Cauchy sequence in XD is convergent. Therefore, XD is a complete metric space. Therefore, XD is a complete metric space. Hence, proof of theorem is completed. Okay, we will stop here. Thank you.